We now have experience with determining the point group of an object. We have some extra practice with determining the point group of an object. And now we are going to see how we can use those point groups to better understand aspects of molecular structure. And so this is using something called a character table that I introduced in our last video and in our last class. And a character table lists a number of different ways in which a single point group can experience these different symmetry elements. And we're going to see what that looks like here in a second. So our learning goals for today is we're going to learn a little bit more about the construction and validation of a character table. And we're going to do this by deriving some simple irreducible representations and learning about how we can validate this. Now, this is a very kind of math heavy version, and I will get out ahead of the game in case any of you are mathematicians and have maybe seen this in a different class, that we are doing a chemistry version of group theory. We are not doing a deep dive into the mathematical version of group theory. All right, so if there's some discrepancies here, it's because we're simplifying this so we can apply it to molecular systems and not understand kind of the ins and outs of group theory. So to get started, we have this compound down here on the bottom right. So this is a dibromonaphthalene derivative. And what I want you to do is figure out all of the possible symmetry operations for the structure and the point group. So pause the video and do that now before we move forward. All right, so hopefully, as you were able to piece this together, you found that there's only a couple symmetry operations that are present in this dibromonaphthalene compound. It has a C2 principal rotation axis, and this is currently sticking out of the drawing surface, right? So this is my Z axis as drawn. And again, the notation, the general, notation for symmetry operations is our principal rotation is placed along the Z axis. This molecule also has an inversion center and a horizontal mirror plane. So hopefully you were able to come up with these three different symmetry operations and then include the identity. So the identity is one that's easy to forget, but it is always there. So we always have to make sure that we account for this E symmetry operation, which again stands for the identity. And so when we look this up, we can figure out the point group for this, right? So again, it has a C2 principal rotation. So that puts us in that puts us past the low symmetry cases. It is not one of our high symmetry examples. It's not tetrahedral or octahedral. And so now we need to look for any other, or if we have a perpendicular C2 rotational axis. And I don't. In fact, all I have is my principal C2 rotation. So this puts me in my capital C point groups. There is a horizontal mirror plane, so we land on C2H as my point group. Now, if we look this up on our character tables, we'll see that we actually have all four of these symmetry operations listed out for us nicely. And these are what we're going to call classes of our symmetry operations. They are grouped up by type. So we have the identity, we have our principal rotation, and then we will have other rotations, and then the inversion center and our mirror planes towards the end. And so you would see this if you look on a list of our character tables. Another important feature is that we actually have the order for our classes, and that's this number in red. So it's implied that this is a 1 for each case here. But as we look at more sophisticated examples, we'll see that it is not always a 1, right? We might have multiple different rotations. We're starting with a relatively small point group just to make our life a little bit easier. All right, so we have the order of our class, we have these different classes of symmetry operations, but what is going on with the rest of this idea of a character table, right? You'll see that this is only the top line if you look at the character table. So what does the rest of that mean, right? How do we build out the rest of this character table? So you would see that there's a bunch of numbers, right, that fall down in here. What do those mean, right? Where do they come from? Right, so how do we build these? And on top of having these numbers, there's a bunch of these, what end up being names for these classes of symmetry operations over on the left, right? These are called mulliken symbols, and we'll talk about how we derive these in a second. And so, well, one of the ways that we can derive our different representations, right, these different lines in this table, that's our character table, is by looking at just the coordinates. So you'll see that to the right, There's a few other columns, one that's coordinates, one that's quadratic, and you might see further higher order polynomials depending on your source for your character tables, where you will pretty much only be using the coordinate and the quadratic columns. And this is actually partly where we can derive some of our characters, right? So this is how we're going to derive some characters. And we're going to use that or derive them using these coordinates. So what we have here in the central box, right? In the central box, these are what we call the characters, right? And if you're looking through our different point group tables that we have access to, there's lots of ones and minus ones. There's some zeros, some twos. If you look closely, you'll see some threes, and we'll get into that as we learn what these characters are and where they come from. So they come from looking at our coordinates and imagining how our coordinates change under these different symmetry operations. So I hope that you feel comfortable with these symmetry operations by now. We've been doing them for a week or two, and I hope you feel comfortable with identifying them in a structure, because now what we're going to do is look and see how our x, y, and z coordinates change under each one of these symmetry operations. So let's start with C2. When we look at what happens for a C2 rotation, again, this is rotating about our z-axis, right? So rotating about this z-axis. What happens for our C2 is that our z-axis remains unchanged, right? Our y-axis moves 180 degrees, right, to be pointed down here. This is where our y-axis ends up. And if we're going to look and see what happens to our x-axis, right, our x-axis also rotates 180 degrees and ends up pointed in the opposite direction. Now, this fact that they are pointed in the opposite direction means that the symmetry of this axis has changed, right? And so what happens is when we're assigning these characters, we're looking at the operation, so in this case our C2, and we're asking ourselves, what happened to my coordinate, right? If my coordinate stayed the same, if it remained unchanged, it gets a 1. So in this case, z is the only thing that gets a 1 for our C2 operation. We notice that both x and y are now pointed in the opposite direction from where they started. So that means that both x and y get a -1. And this is just the rules of how we construct the characters in a character table. Is we perform the symmetry operation and we look and see what happened to the orientation of our axis, right? So our x, y, and z axis here. So I can see that when I did my C2 rotation, x and y switched their directions and z remained the same. So we're going to continue this by looking at our horizontal mirror plane, right? So this is a reflection in the xy plane. And so when we look at this reflection, I can see that my z-axis is the only thing that moves, right? Y and x are contained inside this mirror plane. So the z-axis flipped directions, right? So that means that my z-axis would get a -1, and x and y would both get +1 for these characters. So again, we're just looking at what happens to the coordinates in each one of these symmetry operations, right? Last but not least, we can look at inversion. So again, inversion is where everything travels through the origin and out the other side. So it's really no surprise, right, that when an inversion occurs, each one of our axes is flipped, right? So as drawn, each one of these axes would get a -1. So again, they switch directions, so it's going to get a -1. This is our kind of simplified introductory version of these characters in a character table. Now, lastly, right, we haven't looked at the identity, but again, the identity is the mathematical equivalent of multiplying by 1. And so we can imagine that at least for our axes, right, there's nothing we can do under the identity that would change our axes, right? They all stay in the same position. That means they're pointed in the same direction, and so they would each get a 1. And so I can look at my currently existing characters, and again, I've just described them using these symmetry operations. So I did the operation, I looked to see how my compound or how this axis changed, and then assigned it either a 1 or a -1. So we need to be able to label these rows. And so this collection of characters, right, one entire row of our character table is called an irreducible representation. The way we could think about this is a simplified set, or the most simplified set of the effects of these symmetry operations on a piece of the structure, right? So one row of a character table is called an irreducible representation. The names that we generate for this is in the left-hand column, and these are called mulliken symbols. And these are ways of describing or naming individual irreducible representations. Now, there's a simple set of rules that help us derive these mulliken symbols. So the first step is identify our principal rotation, right? So if our principal rotation is a -1, then the mulliken label is a B, and it starts with a B. If our principal rotation is a +1, then the mulliken symbol is an A, right? So that's the very first step for assigning our mulliken symbols, right? The names to these rows or irreducible representations in a character table. The second step for this is actually looking at our inversion column, right? So this only applies if a molecule has an inversion center. But if it has an inversion center, this determines the subscript, right? If our inversion center is antisymmetric with respect to the with respect to inversion, sorry. So if this is a -1, we have a subscript U that is in our mulliken symbol. This stands for Ungerad, which is antisymmetric, and it specifically relates to the inversion center. If the inversion was a 1, right, if it was a +1 value, this subscript would be a G, right? So it would just be a subscript G if there was a +1 with respect to inversion. So let's look at our next step. So this is not the complete character table. So you can look at the character table for C2H on your list, and you would see that there's 2 more rows. So how can we fill out this character table? How can we extend it and finish what we started and generate this full character table? Well, we need to understand some rules about the way that this works, right? And the way that this works, there's 4 rules that we're going to follow. So the first is that tables must be square. So that means that my number of classes, right, in this case there's 4, has to equal my number of irreducible representations, right? Irreps is one way we can abbreviate this for irreducible representation. And so I can see here that I'm actually missing 2 rows, right? And I can see that I'm missing 2 rows because I only have 2 irreducible representations. Now, where did I only get 2, right? I started with 3. It's because X and Y had the same set. So if we looked at those numbers, we would see that they're identical. We cannot have different irreducible representations, right? We would group them up together and we say that both of them are described completely by the same irreducible representation. So here we are, right? We have our 2 rows in our character table, and now we need to figure out these missing 2 rows. Thankfully, one of our rules for constructing a character table gives us one of these rows directly. And this rule is our rule number 2 that we're looking at down here, that there always has to be one representation that is completely symmetric, meaning everything is a 1. Right, so if we went through here and we were going to label these, right, let me move this stuff out of the way. If we were going to go through and label these, there has to be one representation that is all 1s across the line. So what would we name this, right? So we have our rules for our mulliken symbols. So pause the video for a second and think about what would the mulliken symbol for this particular row be? All right, so hopefully you arrived that this would be, right? So first off, it has a 1 for our principal rotation. So that means that it's a capital A. It is also symmetric with respect to inversion. That means this has a subscript G, right? So this is our A sub G irreducible representation. Okay, so now I'm just missing one, right? I'm just missing one more of these irreducible representations. I've now filled in BU, AU, and AG. And so what we have to figure out now is what is this last row and how can I validate it? How can I confirm that this is in fact a part of my point group, right? Because I can't just make up numbers here. I have to be able to validate and show, right, that this fits within our point group. So this is where we're going to get a little bit heavier on the math side as we start to validate these character tables. It's still just lots of multiplication and addition, so we're not doing any like heavy calculus here, but we are going to investigate how do we construct and validate a character table, right? How do we make sure that a row of a character table actually matches? And this is something that will be important later as we start constructing our own representations, right? Maybe not irreducible, but just representations on their own. So we have two more rules that our character tables must follow. So this is rule number 3 and number 4, right? And the first of these is that irreducible representations must be orthogonal. So what does that mean, right? This is a mathematical term. We think orthogonal, we might think, 90 degrees, where they intersect like we have done, when we're discussing axes and determining point groups. So what does orthogonal mean for a character table? What orthogonal means is that if you add up the product of two rows on this character table, multiplied by the order of the class, it should equal 0, right? It should equal 0. So that means that if I take any two rows and multiply them together, and I multiply by the order of the row, and then add it up, it should equal 0. So what does this look like in a practical sense? So let's validate. Let's look at how this kind of works out, right? So let's say I wanted to make sure that BU and AU are orthogonal. What I would do is I would take the characters, right, the entries in my character table. I'd multiply them by the class order, right, which again is assumed to be 1 here, right? There's not a number written, so we can assume that it's 1. And I would do this for each class, each column essentially in my character table. And so I could see that 1 times 1 is 1. I have 1 times -1 times 1, which leaves me with -1. And I can continue to just go down the line. And then what I would do is I would take all of these numbers that we just derived, right? I would take all of these numbers and I would just add them up. That's the sum here, right? So this R in this equation is the class order. I and J just mean different irreducible representations. So different irreps. And this value chi is the character, right? Or the entry on our character table. So if we were going to multiply these all together, right, this is how we end up where we are. Now we're going to add these together. So we add 1 plus -1 plus -1 plus 1. And that should be equal to 0, right? So now I'm going to add along inside this green box, and I see that this is equal to 0. This is the proof that BU and AU are orthogonal, right? So because this is true, I can say that BU and AU are orthogonal. So this is one of the requirements for this to be a valid entry in our character table, is it has to be orthogonal to the other point groups. You could do the same process looking at all of the irreducible representations together. So if we looked at the entire table, you could do this. So what we're going to do is we're going to put on our thinking hats a little bit, and we're going to kind of make a guess at what this irreducible representation might look like. Right, so we can look at our existing irreducible representations, right? These top 3 were the ones that we've already derived or described. And so now we need to figure out what this 4th one might be. So if we're going to kind of look at this, we would see that so far, my identity operation has always been a 1. And that makes sense because if we are looking at the identity, it would be hard to imagine anything changing about a structure under the identity, right? So the identity is going to be a positive number. And so it makes sense that that would still be a positive 1. If we're looking at our patterns here, right, AG is our completely symmetric case, so it's all plus 1s. But we notice that both AU and BU have 2 negative values apiece, right? They each have 2 negative values apiece. And so we're looking at the way that these are constructed, and it would make sense to think that maybe this other missing irreducible representation would also have 2 negative values. Right, now there's more mathematical ways we could approach this. Again, we could look at orthogonality from the get-go. We could look and see, what the multiple of our order and each one of these ends up being. And so, if we multiplied E all the way down, it would be a positive 1, and we could continue that along the line. But we could make a solid guess, right? Because this has to be a unique entry in our table, right? We can't have redundant lines in our table. That this final case would be a 1, and then a -1, a -1, and a 1 for our final irreducible representation. And so this would get the mulliken symbol BG, because again, it is antisymmetric with respect to our principal rotation axis, C2. And it is symmetric with respect to inversion, right? So it has a 1 under that inversion, that I. So we have to validate this, right? So we need to show that it is, in fact, orthogonal. And so we could pick any one of these different irreducible representations to validate. So we could use BG and AG. We could use BG and BU. Any one of these must be orthogonal, right? So if I picked 2 lines, multiplied them together, and multiplied it by the class order, and added all those values up, it must equal 0. And we can see that that's in fact true. Our last way of confirming and validating an irreducible representation is actually our final rule here, and that's that the sum of the class order times the square of the character for a representation must equal the order of the point group, right? So again, this is kind of a lot of mathematical jargon here, but it's saying that if we take each one of these characters and square it, and we multiply this by the order, right? In this case, again, it's 1 for each one of our classes for our symmetry operations here, that this must equal H when we add them all together. So we can go ahead and kind of run through that mathematical process for this new entry in our character table. And we see, in fact, that we end up with this working out, right? What ends up happening when you square these is that the negative ones become positive ones. And so when these are squared and multiplied by the order, you have 1 plus 1 plus 1 plus 1, right? Which equals 4, which is the order for our point group. And so now we've validated that this point group is, in fact, a part of our character table. And we could look at our character table for C2H and find these 4 different irreducible representations, right? We would see these 4 different irreducible representations in that point group. And so we can kind of confirm that our work makes sense, right? We can confirm that our work fits. So why do we care so much about these irreducible representations? How is this going to tell us anything about chemistry, right? That might be what you're thinking right now, because all we've done is describe these axes. We've described some other ways of generating these irreducible representations that exist on a table. But why on earth does this relate to chemistry? Well, it relates to the shapes of our molecules. And when we think of shapes, one of the things that probably springs to mind is orbitals. And this is going to be the first application of group theory that we're going to be getting into over the next week or so. Because when we think about the symmetry of an orbital, right, an s orbital actually has symmetry that matches the AG irreducible representation. No matter what we do to an s orbital, it remains unchanged. If we rotate a sphere, we still end up with an indistinguishable sphere. If we were going to invert this sphere through the origin, we end up with an identical sphere. So this s orbital, right, has this completely symmetric symmetry, right? So we would say that s orbitals match the AG symmetry within this point group. We can extend this analogy and we can say that both the x and y, or x and y axes, actually match what happens with the px and py orbitals. So both the px and py orbitals have Bu symmetry under this point group. So if we think about an axis, so if we're looking here at our x-axis, we have our origin, and this extends towards negative x. And we think about what an x orbital or px orbital looks like, right? It's that nice dumbbell shape with one lobe being shaded. And so this symmetry of this orbital actually matches the symmetry of the axis, right? We could think of the unshaded part as the, quote unquote positive lobe, and then we have the shaded piece as our negative lobe. Now this is not actually what's happening physically, but this just helps us imagine and align a p orbital with our x-axis. So px and py match the Bu irreducible representation. It describes what happens to them under these different symmetry operations. Similarly, the pz orbital, which is different than x and y, is described by the Au irreducible representation, right? So there's a lot that's been going on here as we're describing these different shapes, but we can at least start to populate and validate these entries in our character tables. And we are going to be relating these directly to molecular structure. So let's revisit our learning goals, right? So we can look up and find character tables using our chart, right? Our giant list of character tables that was provided to you. We can derive some of these simple irreducible representations for our coordinates. This is something we're going to be applying moving forward as we look at orbitals and we start to dig a little bit deeper into how we can construct what we call reducible representations. In addition to deriving these irreducible representations for coordinates, we can apply the rules of character tables to determine any missing representations. So this is how we filled in the AG and the BG irreducible representations. We can also validate these, right? So they must be orthogonal, right? So that was where we compare two lines on our character table. And they must also equal the order when we square the character and multiply it by the class order. So there's a little bit more math involved here than we might be used to seeing, right? We can also talk about how we can name these irreducible representations using these mulliken symbols. So moving forward, if I were to tell you that we had a BG type symmetry, you would know that no matter what we're talking about, it is antisymmetric with respect to the principal rotation axis, and it's symmetric with respect to inversion. That mulliken label actually tells us a lot about the symmetry of a given line, of a given object or substructure within our point group. So I'm going to leave you with a challenge, something to think about a little bit. And thankfully, it's not going to be derive these character tables over and over again. What I'm going to ask you to do is think about the structure of ammonia, right? This is a molecule that we figured out its point group already, right? We've done this one before. We've talked about the point group here. So what I want you to do is determine the point group for ammonia and look up the character table. And I don't want you to try to explain the character table, right? It has some oddities that we haven't talked about yet that we'll get into in the future, right? It has a different mulliken symbol that we don't know how to explain. It also has a 0 on the character table, which we do not know how to explain yet. But what I want you to do is I want you to use rules 3 and 4 just to validate each irreducible representation. So when you're looking at those lines, how can you validate using orthogonality? And how can you validate that it matches the order of the point group? So make sure that you understand how to do that for ammonia. And when you come to our next class, we'll do some more practice with character tables. We'll dig into more of the anatomy and structure of these character tables and think and start to apply them towards molecular and chemical systems. All right, thank you.